So we've got two functions, f of x is not excellent. F of x equal to x cubed minus 2x. And g of x equal to 4x minus 5. And what we want to do is well, first we'll just talk about like evaluating functions. So we've talked about evaluating functions before. Like I can find f of 2, right? When I'm trying to find f of 2, I'm just substituting 2 in for each value of x, or for each occurrence of x, I should really say. So we get 2 cubed minus 2 times, which is going to be 8 minus 4, which is 4. I care less about the value. I care more about actually figuring out what it is. In a similar way, I could find g of, say, 1. G of 1 is going to be 4 times 1 minus 5. And again, right, wherever I have an x, I'm just replacing x with whatever is inside the parentheses here. In this case, I get 4 minus 5, which is negative 1. But then I can find compositions of functions, meaning I can ask what is, I should get a third color here. I can ask something like, what is f of g of 1? And typically, I feel like the easiest way to find something like this, f of g of 1, is to first figure out what the inner part is. So f of g of 1, well, we know what g of 1 is. G of 1 is negative 1. So this is equal to f of g of 1, which is just negative 1. And then f of negative 1 we can plug into the function. So it's going to be whatever's in there cubed minus 2 times whatever's in there. I feel like all my pens, every week, it's like, oh, the pens are dying. So that's going to be negative 1 cubed minus 2 times negative 1. Negative 1 cubed is negative 1. And negative 2 times negative 1 is plus 2. So negative 1 plus 2 is going to be 1. So f of g of 1 happens to be 1. Or we could find g of f of 4. And so, again, to figure this out, I'm going to figure out what f of 4 is first. So I'm going to say, okay, f of 4 is 4 cubed minus 2 times 4. I'm just replacing the x's with the 4's. 4 cubed is 64. 2 times 4 is 8. 64 minus 8 is 56. So g of f of 4 is going to be g of 56. And then g of x is 4x minus 5. So g of 56 is 4 times 56 minus 5. 4 times 50 is 200. 4 times 6 is 24. 4 times 56 is 224. Minus 5, that's going to be 218. So you don't have to do it this way, but when I compose functions, I typically think about doing it from the inside out. Meaning I'm looking at what's happening inside first, and then I'm figuring that out, and then I'm applying the outer function after that. You don't have to do it that way. You certainly could, if you wanted to, find something like, I don't know, you could find f of g of 3 by first saying what f was. So again, same functions, right? F of x is still x cubed minus 2x. G of x is still 4x minus 5. I can say that f of a thing, so f of x is x cubed minus 2x. So f of a thing is thing cubed minus 2 times the thing, where the thing is g of 3. But then I have to figure out what g of 3 is. Well, g of 3, g of x is 4x minus 5. So g of 3 is 4 times 3 minus 5 cubed. Minus 2 times g of 3, which is 4 times 3 minus 5. To me, this feels like a lot more work. This feels like a lot more writing. I would rather have figured out what g of 3 was first and figured out that g of 3 was 12 minus 5, which is 7. And just written this as, I don't want to cube this out like it is. I want to say, oh, 12 minus 5 is 7. 7 cubed minus 2 times 7. I'm still really kind of working from the inside out. It's just kind of how I do it. What's 7 cubed? Well, 7 squared is 49. And 49 times another 7 is, well, 50 times 7 is 350. So 49 times 7 is 1 7 less, which is going to be 343. So 343 minus 14, which is going to be 329. And sometimes we don't even want to find the composition of functions at a particular value. We might want to find something like, so I'm going to go back to this side actually. I might want to find something like f of g, or sorry, g of f of x. So in this one, I'm definitely going to use the color. So I'm going to find g of f of x. And again, I really like to think of it as the inner function first. So I'm going to think of this as g of whatever f of x is, which is x cubed minus 2x. And then g says, take whatever's in the parentheses. So g of x is 4 times x minus 5. So g of parentheses is 4 times parentheses minus 5, where the thing in parentheses is x cubed minus 2x. And then you could simplify it a little bit, right? You could say, okay, that's going to be, I'm going to distribute the 4. You can get 4x cubed minus 8x minus 5. That's a 5, believe it or not. And that would be the function g of f of x. Or the composition g of f of x. Let's look at the composition the other direction. Let's look at, say, f of g of x, which is going to be a little more complicated. So f of g of x, so again, f of the thing, the inside thing is 4x minus 5. So this is going to be f of 4x minus 5. And then f of x is x cubed minus 2x. So f of a thing is going to be the thing cubed minus 2 times the thing, which in this case is going to be 4x minus 5 cubed minus 2 times 4x minus 5. Yeah, we could multiply this out. I don't really think we need to. That's not really the point. Yeah, so I'm not going to multiply it, although we certainly could. Oh, I did. Then I scroll down and notes say I totally multiplied it. So I'll remind you, if you want to multiply out something cubed, right? We've seen this with the, oh, have we seen this? I don't know. Anyway, I'll show you, if you're cubing something, the pattern for a minus b cubed is a cubed minus 3a squared times b plus 3a times b squared plus b cubed. Oh, sorry, minus b cubed. So in this case, my a is the 4x and the b is the 5. This ends up equaling 4x cubed, which is going to be 64x cubed, minus 3 times 4x squared, which is 16x squared, times 5, plus 3 times 4x times 5 squared, which is 25, minus 5 cubed, which is 125, minus 2 times 4x, minus 2 times minus 5 is plus 10. And then you can put this all together and you get, let's see, 64x cubed. This is going to be 16 times 5 is 80. 80 times 3 is negative 240 x squared. 4 times 25 is 100 times 3 is 300. So 300x minus 8x gives me 292x. Minus 125 plus 10 is minus 115. But again, don't sweat that last part so much. It's not really what's important. The important part is being able to compose the functions and know which one goes inside the other one. So composition, g of x or g of x. I should also point out some people, not me, but some people, some books prefer to write this as g circle f of x like that. It means the same thing. We read this as g of f of x or g composed of f of x. So one of the reasons we like to talk about composition of functions is because it's how we define if functions are inverses. So we say that two functions are inverses. Two functions are inverses if the following is true. F of g of x is equal to g of f of x is equal to x. So I should point out, in the notes that are online, it actually doesn't say it's equal to x. It should actually be equal to x. There are some functions that when you compose them with each other, they are equal to each other without being equal to x. Those are not inverse functions. So g of f of x equals f of g of x. Sorry, f of g of x equals g of f of x equals x. Those functions are inverses. So here's an example. Here's not my favorite example. So example, f of x equal to the square root of x and g of x equal to x squared. Now these, I should point out, are not inverses everywhere. These are inverses for any non-negative value of x. But if x is negative, things don't really work out so well. Well, let's take a look and see. So if I look at f of g of x, that's going to be f of x squared, which is going to be the square root of x squared. Now let me ask you guys, what's the square root of x squared? You're right, Aaron. Well, I should say, yes, you're right, Aaron. In this particular context, the square root of x squared is equal to x. And I do want to say that more generally, the square root of x squared is actually equal to the absolute value of x. It's just that here we're only talking about x being positive, so that the absolute value of a positive number is just the positive number. That's why this actually doesn't work if x is negative, right? If you take the square root of negative 5 squared, you don't get negative 5 back. You get positive 5. And g of f of x is equal to g of the square root of x is equal to the square root of x quantity squared. And if you take a number and you square root it and then you square it, you get back the number you started with. The whole idea with inverse functions, and I really want you guys to take this to heart, is that inverse functions, one of them does something and then the other one undoes it, right? F of x takes the square root of a number. So let's say you started with 9, the square root of 9 is 3. And then if you put 3 in here, g undoes what f just did. It gives you back the number you started with. So I plugged in 9, square root of 9 is 3. I took that 3 and plugged it in here, and 3 squared got me back to 9. So, right, f does something, g undoes it, and we get back to the x value that we started at. That is the whole idea with inverse functions, is that they completely undo what the other one did. Another really good example of inverse functions are the exponential and logarithmic functions. And I'm out of room here. So two more inverse functions are, there's lots of inverse functions, but another very common example of inverse functions are f of x equal to, what have we got here? E to the x and g of x equal to the natural log of x. Or if you prefer, another example, f of x equal to 2 to the x and g of x equal to the log base 2 of x. These functions undo each other. For example, if I put in x equal to 3, f of 3 is going to be 2 to the third, which is 8. If I then take that output of 8 and put it into g, g of 8 is going to be log base 2 of 8, which is 3. It undoes what f did, right? It gets me back to exactly where I started. So we can say for each of these is that for the green ones, f of g of x equals f of the natural log of x, which equals e to the natural log of x. And we know that e to the natural log of x is just x. Right? Those functions I don't really want, so I would encourage you not to say that they cancel out. I would really encourage you to say the words that they undo each other, because it's not so much a canceling as an undoing. One of them does something, the other one undoes it. And also the other way, g of f of x is g of e to the x, which is the natural log of e to the x. And you can either just say they undo each other, or you can even use the power rule, right? Bring down the x and say it's x times natural log of e. But the natural log of e says e to what power equals e? Oh, e to the first power equals e. That's a 1. So that's going to be x. Same thing is true if you change the base, right? These are really the same statements. It's just that here the base is e for the green ones, and here the base is 2 for the red ones. We can say the same exact stuff. That f of g of x is f of log base 2 of x is 2 to the log base 2 of x. And so whatever x is, you're saying, okay, 2 to some power equals x. And then you're saying 2 raised to the power, that if you raise 2 to that power, you get x. Well, then you're going to get x. And similarly, g of f of x is g of 2 to the x is log base 2 of 2 to the x. Of 2 to what power equals 2 to the x? Yes, you're right, Aaron, it's x. 2 to some power equals 2 to the x, that power has to be x. So I really want to stress, inverse functions, they undo each other. G does something, f takes you right back to where you started. And the place we start is x, right? If I'm thinking from the inside out, I'm starting at x. G does something to that x. F does something else that gets you back to where you started at. Like 3, for example, right? G of 3 is that. Like 8, right? X is 8. G of 8 is log base 2 of 8, which is 3. And then f of 3 is 2 to the third, which gets you back to 8. All right. So those are some pretty typical examples of inverse functions, or I should really maybe some more standard examples. Those are functions that we can even just kind of, I mean, especially with the square and the square root, it's like, oh yeah, one number squares it, the other number square roots it, they undo what the other one did. But let's look at an example that's a little bit easier to kind of visualize. Oh, no. One sec. That water almost went down the wrong way. Okay, so anyway, I'm all right. Let's look at, I'm all right, he says he's still coughing. Okay, yes, let's look at the following two functions. So f of x equals 3x minus 4 divided by 2. And one of the things I've noticed over the years about inverse functions is the kind of the ones that are a little bit less complicated, like this one. You can almost kind of talk out how to undo what was done. This is not really super like methodical. It's just kind of like, oh yeah, I've seen this thing. Oh, also I should do, got a lot of light on here. 1 second. Turn down that. Hopefully it's easier to see the greens with the setting turned down there. So here's what f does. F takes x, first multiplies by 3, then adds 4, then subtracts 4, then divides by 2. To do the inverse, I'm going to undo all those things in the reverse order. So instead of first multiplying by 3 and then subtracting 4 and then dividing by 2, I'm going to undo dividing by 2. So I'm going to multiply by 2. I'm going to undo subtracting 4, so I'm going to add 4. I'm going to undo multiplying by 3 by dividing by 3. And that is the inverse function. Let's look at an example. Let's look at f of, I don't know, let's pick something easy like f of, I don't know, 6. F of 6 is going to be 3 times 6 minus 4 over 2. 3 times 6 is 18. 18 minus 4 is 14 over 2, which is 7. So f takes an input of 6 and gives an output of 7. G should undo that. G should take this output of 7 as its input and spit back out what we started with. So G of 7 is 2 times 7 plus 4 over 3. So 2 times 7 is 14 plus 4 over 3. That's 18 over 3, which is 6. So they undo each other. And you can kind of see, oh yeah, they undid the, right? So right, this one I did 3 times 6 was 18, then subtracted 4 and got 14, then divided by 2. Here I took my 7, I first multiplied it by 2 to get the 14 back, then I added the 4, subtracted to get the 18 back, and then I divided by 3 to get the 6 back. But we can also see this just, so I should point out, and this is really important, if I ask you guys to show me that these functions were inverses, it would not be enough just to do it for one specific numerical example. Right? It's not enough to say, oh, f of 6 is 7 and g of 7 is 6, boom, done. We have to actually show it's true for any x. And I have to show it both ways, meaning I have to show that both f of g of x is equal to x and that g of f of x is equal to x. Let's do f of g of x first. So f of g of x is f of 2x plus 4 over 3. And then f of x is 3x minus 4 over 2. So f of thing is 3 times thing minus 4 over 2. So it's going to be 3 times that minus 4 over 2, where this is what's going right there. Now, here's what I don't want to see. I've seen people do too much canceling at once. People like can't say, okay, like I've seen people do all the canceling, like say 3's cancel, 4's cancel, 2's cancel. The problem there is it's not really specific about what order things are being canceled. So I would really like to see just kind of one canceling at a time. Meaning, okay, first these 3's can cancel. Then I can rewrite this as 2x plus 4 minus 4 over 2. Then 4 minus 4 is 0. Then this is 2x over 2. 2's cancel, you get x. I really want to see that much work. And then let's go the other way. Let's find g of f of x. I guess I can erase this part here. So g of f of x, same idea. G of f of x is going to be g of this 3x minus 4 over 2, which is going to be now g of x is 2x plus 4 over 3. So g of some stuff is 2 times my stuff plus 4 over 3. And then that's going to, oh, I should actually fill in what goes in there, right? So this goes in there. Then I can cancel the 2's. So I get 3x minus 4 plus 4 all over 3. And then I can cancel the 4's. And I get 3x over 3, which is just x. So great. We showed that they're inverses. F of g of x and g of f of x are both equal to x. Okay. So the whole idea with inverse functions is that they interchange the role of the input and the output. In this function, we inputted 6 and we got out 7. In this function, we inputted 7 and we got out 6. So a lot of people kind of view that as the x's and y's switching roles, which is true. And we've, in fact, seen that for logarithmic and exponential functions especially, right? If you recall, we graph a couple things here. Sure. So just as a reminder, here's the function essentially y equals 2 to the x, or f of x equals 2 to the x. And here's the function g of x equal to log base 2 of x. And I'll remind you some of the coordinates on these graphs. On this graph, you have the coordinates 0, 1, and 1, 2, and 2, 4, and 3, 8. And on this graph, you have all the points where the x, y values are switched. Right? Instead of 0, 1, you have 1, 0. Instead of 1, 2, you have 2, 1. Instead of 2, 4, you have 4, 2. And there's this really nice symmetry across the line y equals x. These points are really kind of just, you can map them to each other like that. So inverse functions undo each other. They interchange the role of x and y. And graphically, they're reflections of each other across the line y equals x, which makes sense because if you reflect across the line y equals x, that is literally interchanging the values of x and y. Okay, so how do we find an inverse function? Well, we start off by interchanging x and y because that's what's happening. You're interchanging x and y. So let's look at the following. Let's look at the function f of x equal to, what have I got here? 4x cubed plus 1. And we're going to find the inverse. And to find the inverse, I think of it as a 4-step process. It's really three kind of bullshit steps and one real step. So there's 3 steps that are kind of just like, okay, you're just doing things. So step 1. So I should say, right, this is to find the inverse. Sorry, not to use inappropriate language, but there's no better word to say there than what I said. So yeah, 3 BS steps, 1 real step. Step 1. Rewrite this using a y instead of f of x. So rewrite it as y equal to 4x cubed plus 1. This is not absolutely necessary, but it's easier to work with y than it is to work with f of x. Because in step 2, we're going to interchange x and y. In fact, let me write out the steps next here. So we're going to write x equal to 4 y cubed plus 1. And I really should say, so back on right here. So first, replace f of x, or whatever your function is called. It might be g of x, it might be q of x, it might be k of x. Replace f of x with y. Step 2, all the y's become x's, all the x's become y's. There should only be one y, but there might be multiple x's. So interchange the role of x and y. And I really want to stress again, if there are multiple x's, all of those x's each become y. There should only be one y, it's going to become x. And then the third, so again, these first 2 steps, they're kind of like nothing steps, right? We haven't really done much, but they're still important. I should point out though, this step is pretty key, even though it doesn't feel like you're doing a lot. This is when you've actually changed it, right? Here, if you put in x equal to 1, you would get y equal to 5, right? Because 4 times 1 plus 1 times. Here, now if you put in x equal to 1, what? Right? Here, if you put in y equal to 1, you get x equal to 5. So you interchange the roles of x and y by interchanging the roles of x and y. Step 3 is the step where stuff actually happens. Solve for y. So this is where you actually have to do the work. So we're trying to isolate y. So I'm going to subtract 1. So x minus 1 equals 4y cubed. Then I'm going to divide by 4. X minus 1 over 4 equals y cubed. And then I'm going to take the cube root of both sides. So that you could also say raise both sides to the 1/3 power. But I'm going to write this as the cube root of x minus 1 over 4 equals the cube root of y cubed. But the cube root of y cubed is just y. And I will point out it's not even the absolute value of y. It is really actually just y. If it's a square, so, and again, I should say a little bit more about this. Square root of x squared is the absolute value of x. 4th root of x to the 4th is the absolute value of x. Even root of x to the same even power is going to be absolute value of x. So if you have the 6th root of x to the 6th is the absolute value of x. But if you have an odd root, like the 5th root of x to the 5th, it's just x. And the reason that is because you can't take the even root of a negative number, but you can take the odd root of a negative number. So that's why it kind of works out that way. So here we just get y. That's your third most important step. And then the last step, which again is kind of just a nothing step, is to replace y with f inverse, because that's the name that we give the inverse function. So step 4, rewrite it. Instead of writing y equals a thing, we write it as f inverse of x equals the cube root of x minus 1 over 4. Again, so this looks like f to the negative 1 power of x, but we always say it as f inverse of x. And it's not the same as 1 over f of x. It's very different. Okay, anything else I want to say about this? We could check that they're inverses by composing them, right? You could say f of f inverse of x, and you would get x. And we can also kind of talk this one out as well, meaning the original function takes x, cubes it, then multiplies it by 4, then adds 1. The inverse undoes that. Takes your x, first subtracts off the 1 that you added, then divides by the 4 that you multiplied by, then cube roots to undo the cubing. So it's exactly undoing all the things we did there in the reverse order. So that's your 4-step process for finding an inverse. Rewrite it as y equal to the thing, switch x and y, solve for y, that's the hard part, and then rewrite it as f inverse or g inverse, whatever your function is called. So let's look at another example. So let's say our function is, I'm going to call it g instead of f. Let's call it g of x equal to 2x plus 3 over x minus 4. A rational function. And just to point out a couple things, I want to point out that for this rational function, what's the vertical asymptote for that rational function? X equal to what?
4.
Sorry, I know you said something I didn't quite hear because the volume was down. Yeah, exactly, 4. And what's the horizontal asymptote for this function? Y equal to what? Yeah, exactly, 2. Okay, we'll come back to that, but I definitely want to say that. Anything else I want to say there? I don't think so. No, okay. So let's go through the process of finding the inverse. So step 1, replace that g of x with a y. So y equals 2x plus 3 over x minus 4. Step 2, interchange the x's and y's. So this y becomes an x, and all these x's become y's. Step, all the x's become y's. Come on, get it together, James. And then we solve for y. Now solving for y is difficult here. I want to show you guys a mistake that people make, but I don't want you to do it. So don't write this down if you're taking notes for a second, and then I'll show you what to do. So first up, I'm going to multiply both sides by y minus 4. So I'm say x times y minus 4 equals 2y plus 3 over y minus 4 times y minus 4. The whole point of doing that is to get rid of the denominator on the right-hand side. So far, everything's fine. So we got x times y minus 4 equals 2y plus 3. Coming right over here in red, the things we shouldn't do. So here's what I've seen people do, and it is wrong. I understand why you want to do this. I've seen people subtract 3 to say x times y minus 4 minus 3 equals 2y, and then divide both sides by 2. So that they've solved for y, they've gotten y equal to x times y minus 4 minus 3 over 2. And the problem here is that the y has to be a function of x. You can't have y's in your answer if you're solving for y. So when we're solving for y, we have to isolate y, meaning we have to get all the y's kind of together before we can solve for y. I'm going to erase that because it's wrong. Here's what we really have to do instead. When you have multiple y's, you have to get them all to one side. And to be able to do that, we have to distribute the x here. So I have to multiply x times y and x times -4. So I end up with xy minus 4x equal to 2y plus 3. And now our job is to group all the things that have y on one side and all the things that don't have y on the other side. It doesn't matter which side you pick. Let's bring all the y's to the left. So I'm going to have xy minus 2y equal to, I'm going to bring all the not y's to the right. So I'm going to add 4x to get 4x plus 3. Now I'm going to factor out a y. That's why I brought all the y's to one side. So I could factor out a y. And let's see, if I factor out or divide out a y, I'm left with an x minus 2. So I've got y times x minus 2 equals 4x plus 3. Now I'm going to divide by x minus 2 to get y equal to 4x plus 3 over x minus 2. And then lastly, again, kind of a nothing step, we would write it as it's g. So we write it as g inverse, which looks like g to the power of -1, but we say g inverse of x equals 4x plus 3 over x minus 2. And that is your inverse function. Now I want to point out something kind of interesting. For this inverse function, what's the vertical asymptote? Yeah, thanks for repeating that too. Exactly. The vertical asymptote is x equal to 2. And you should really write, you shouldn't just say 2, you really should say x equal to 2. And your horizontal asymptote is what? Right, exactly. It's y equal to 4. What I want to point out is they've exactly interchanged roles, which makes sense, right? If we interchange the role of x and y, then if a vertical asymptote is x equals 4, and you interchange x and y, you're going to get a horizontal asymptote of y equal to 4. And if you have a horizontal asymptote of y equal to 2, and you take the inverse function, you interchange x and y, you're going to get a vertical asymptote of x equal to 2. So this is often how people, what I'm really saying here, although I'm not actually saying it, is that when you interchange x and y, you swap the domain and the range of a function. So this function has a domain that includes everything except for 4, right? Because x can't equal 4. This function has a domain of everything except for x equal to 2. So the domain of this function, which doesn't include 2, is the same as the range of this function. The range of this function does not include 2. If you graph this, you'll see it never equals 2. And vice versa. The domain of this is everything but 4. The range of this is everything but 4. Kind of neat. It's actually how people find the range of functions. If a function is invertible, they often find the range of it by finding the domain of the inverse function. You can't always do that, though, because not every function has an inverse. Okay, let us talk about the difference quotients. It's very gray and rainy. It's about raining right now, but it definitely rained earlier over here. So, difference quotient. A secant line is a line that goes through 2 points on a graph. So for example, let's see, how do I want, yeah, sure. Nah, come on, this pen is outlived its usefulness. So for example, if I have a graph that maybe looks like this, where'd this nice pen come from? Beautiful. Here's my graph, I'm gonna call it f of x. And let's say I've got a couple points on the graph, like this point here and this point here. This is the point A with a value of f of A. This is the point B with the value of f of B. Then the line that goes through those points, I should have drawn the line first and then made the points up. Let's see if I can make this happen here. Close enough. That line there, this is the secant line. Or I should say a secant line, right? Because the secant line is any line that goes through two particular points on the graph. And importantly here, and in fact, let me label these points. And I label them, but this point is B comma f of B. This point is A comma f of A. The slope of the secant line, we know how to find the slope between 2 points. The slope is the difference in the y's, so it's f of B minus f of A, divided by the difference in the x's, which is B minus A. And that is one way of talking about the difference quotient. The difference quotient of a function is really just the slope of a secant line of a function. However, we like to write it slightly differently. So what we often do is we actually often give these things different names. Instead of calling this point A and this point B, and this f of A and this f of B, people like to call this x. And they like to call this x plus h. So instead of this being f of A, it's f of x. Instead of this being f of B, it's f of x plus h. So this point is x f of x. This point is x plus h comma f of x plus h. And the slope between those 2 points, instead of being f of b minus f of a over b minus a, another way to calculate the slope if we call the things different names is f of x plus h minus f of x all over x plus h minus x. And we can simplify the denominator because x plus h minus x, the x's cancel. And so when we're talking about the slope of a secant line, one way to think of it is this way. It's difference in the y's or difference in the x's, f of b minus f of a over b minus a. But another way, the way that people often, when they say the difference quotient, actually referring to this, they're saying, oh, it's f of x plus h minus f of x all over the difference, which is just h. So if someone says find the difference quotient of some function, they mean find this and simplify it. Don't worry, I've been writing it down. This is a concept that definitely is going to come up in calculus a lot, no matter if you take the 16 or the 17 or the 21 series. The difference quotient is a kind of a big deal. So again, the difference quotient of a function, right? It's literally called the difference quotient because it's the quotient and each of the top and the bottom are differences. So it's f of x plus h minus f of x all over h. So for example, I could ask to find, say, the difference quotient. So typically the words you say are find and simplify the difference quotient for the function, let's say f of x equal to 5x plus 3. And here is going to be what's going to happen every time. Well, we're going to start off by writing, okay, we're going to get f of x plus h minus f of x all over h. And just the killing black pens here. They're all dying. All these pens. All of them. My blue pens, my black pens, my red pens are all just toast. Okay, so this is going to be f of x plus h. So my function f of x is 5x plus 3. So f of x plus h is going to be 5 times x plus h plus 3. There's my f of x plus h minus Sorry, I'm like 5x plus 3 all over h. And here's what we expect to happen every time we do this. That h in the denominator, we should be able to make it cancel out. So let's see what happens here. I'm going to distribute the 5. We get 5x plus 5h plus 3. Distribute the minus sign, and you get minus 5x minus 3 all over h. Before we can cancel out the h in the denominator, we have to cancel out all the not h things in the numerator. So they should cancel out. 5x and negative 5x cancel. 3 and negative 3 cancel. So we're left with 5h over h, and then h over h cancels, and you get 5. So here, the difference quotient is 5. The slope between any 2 points on that function would be 5. Let's do another example. Let's do like 2 more examples, really. So let's look at a function that's not just a straight line. The time. Okay, well, maybe one more example. I got 2 minutes. So let's look at this example. F of x equal to 4x squared plus 5x plus 1. So again, we're going to start with this. And you don't have to write this every time. I like writing it because it reminds me of what I'm doing. So f of x plus h is going to be, right, f of x plus h, I can even write off to the side here. Right? F of x plus h is 4 times blank squared plus 5 times blank plus 1. It's 4 times x plus h squared plus 5 times x plus h plus 1. So we're going to get 4 times x plus h squared plus 5 times x plus h plus 1. That's my f of x plus h minus, and you do want parentheses, so you remember to distribute the minus sign, minus your f of x, 4x squared plus 5x plus 1, all over h. We have to multiply this out to be able to simplify it, or you can't just start canceling stuff yet. So let's see. You get 4 times x plus h squared is x squared plus 2xh plus h squared. 5 distributed is going to be 5x plus 5h plus 1. Distribute the minus sign, the minus 4x squared minus 5x minus 1 over h. A couple things cancel right now. I can cancel a 5x and a negative 5x, a 1 and a negative 1. But I can't cancel the 4x squared yet because I haven't distributed this for it. I see someone's writing 8x plus 5. I'm not sure what you mean. Oh, I do know what you mean. You're mostly right, Jonathan. You're not quite right because I know. So Jonathan is saying that the answer is 8x plus 5 because that's what the derivative of this is. We're not quite calculating the derivative. And I'll show you the difference and I'll talk about why it's different. And I know we're out of time, but I'll finish this real quick and then we'll be there. So distributing the 4, I get 4x squared plus 8xh plus 4h squared plus 5h minus 4x squared all over h. The 4x squareds cancel. The rest of the terms have an h, so I can factor out the h. So I'm left with, I factor out the h. Here I'm left with an 8x. Here I'm left with a 4h to the first. And here I'm left with a 5. Right, because if I distributed that h back through, I'd have 8xh plus 4h times h is 4h squared plus 5h. Cancel these h's, and my final answer for the difference quotient is 8x plus 4h plus 5. And that's my final answer. Why is it my answer 8x plus 5? Because I still have this 4h. The difference between my answer and what Jonathan is saying, which is the right idea, because eventually when you guys take calculus, that's definitely where you're going, is that when we look at this expression later on, when we're taking calculus, either 16 or 17 or 21, what we're going to end up doing after we do all the simplification is then we're going to take the limit, which I know we haven't talked about. We're going to take the limit of this expression as h goes to 0. And so we're going to let this h value go away. But for now, 8x plus 5 is not the right answer. 8x plus 4h plus 5 is the right answer for the difference quotient. Just be careful because there is a difference, pun not intended, between the difference quotient and the derivative.